Hello friends, now we will start the new chapter, Method of Induction and the Binomial Theorem. Now I had taken the first exercise 4.1. I had explained all the examples in a very simple language. I hope that you will understood all the examples. Now let us start the exercise 4.1. Now let us start the chapter number 4, Method of Induction and Binomial Theorem. In this chapter, there are the two parts. First is the method of induction and second is binomial induction. Now for the method of induction, you have to remember the following 4 steps. That is, if any proof that is there, then you have to follow the following 4 steps. Then what is that principle of mathematical induction? What is the principle? That is first is, that is in first step, it is called the foundation. Principle of, what is the principle of mathematical induction? That is, you have to follow the following 4 steps. In this step, to prove it is true for n is equals to 1. Whatever that LHS and the RHS you have given, prove that that is a substitute n is equals to 1 in n LHS and also n is equals to 1 in RHS. Then LHS is equals to RHS. Now the step number 2, assumption. To assume that is a P of n is true for n is equals to k. Now step number 3, that is a succession. To prove that P of n is true when for n is equals to k plus 1, and this is important steps. In these steps there are some calculations, intelligent calculations are there that you have to perform, and the last is induction. That is, from the above 3 steps we conclude that the given result is true for small n belongs to capital N and whatever that included. That is, P of n is true for all n belongs to the set of natural number. These are the steps included. Now see this, the principle of mathematical induction. Step 1, steps 2, steps 3 and the step 4. First is foundation, assumption, succession and induction. Foundation, prove that it is n is equals to 2 is true. Then assumption, it is true for n is equals to k, and the succession, that is, we perform the calculation in the step number 3, and that is important. And the step number 4 is for the conclusion. Now we will start the exercise 4.1. Prove that by the method of induction, for n belongs to capital N, 2 plus 4 plus 6 dash dash plus 2n is equals to n in bracket 2n plus 1. Let P of n is equals to 2 plus 4 plus 6 plus dash dash plus 2n is equals to n in bracket n plus 1. For all small n belongs to capital N. Now the step number 1. It is called the foundation. For n is equals to 1. Now for n is equals to 1, here see this LHS. The first term is 2. Now consider the RHS. What is RHS? That is n in bracket n plus 1. Put n is equals to 1. That is 1 into 1 plus 1. That is the 2 into 1, which is equals to 2. Then you will get LHS is equals to RHS. LHS 2 आहे आणि RHS देखील 2 आहे. LHS भी 2 है और RHS भी 2 है, इसलिए LHS is equals to ये RHS हो चुका है अभी. Therefore LHS is equals to RHS. Some of my friends say that sir talk in Hindi also. That's why I'm trying to speak in Hindi. Now यहाँ से हम देख सकते हैं कि LHS में 2 है और RHS में भी 2 है. Therefore, the first step is LHS is equals to RHS. Now the step number 2, second step देखेंगे अभी. इनमें assumptions होता है. That is, we put here n is equals to k. हम n की जगह पे k सब्स्टिट्यूट करते और assume करते. This is true for n is equals to k. For some k belongs to set of natural number. That is, we assume that हम assume करते हैं यहाँ p of k is true. Let us assume that for some small k belongs to natural number, p of k is true, and again we write our given statement, and in this statement we only replace n by k. Therefore 2 plus 4 plus 6 plus 2k is equals to k in bracket k plus 1. Now this step is very important, and this is called the succession. To prove or that is to prove p of k plus 1 is true, that is 2 plus 4 plus 6 plus the first term will be here 2k, and the second term will be k is replaced by k plus 1. Now see this, very important. This is p of k. I'm writing here. Now the next is very important. K is replaced by k plus 1. That is a 2 plus 4 plus 6. 2k plus 2k plus 2 in bracket k plus 1. This is important. Now see this, all of you. What is here? That is a 2k. What is the next term? Here k is replaced by k plus 1 and equal to. What is the next here? Again here k is replaced by k plus 2. And again here this k is replaced by k plus 1, and overall it becomes k plus 2. Now see this here. K plus 2. This is very important step. That is, what will the next term? This k is replaced by k plus 1. And what is the next step? This k is replaced by k plus 1, and this k is replaced by k plus 1. It becomes k plus 2. Now 2 plus 4 plus 6 plus dash dash up to the 2k. This is treated as the value that we have seen in the above. Now see this here. That we take the value of 2 plus 4 plus 6 plus 2k from the above step. Its value is a therefore LHS therefore the value of the 2 plus 4 plus 6 plus dash dash plus 2k is a k in bracket k plus 1 plus 2 in bracket k plus 1. Now from these two terms, this is from 1, we substitute here. What is here? The value of up to the underlines is treated as k in bracket k plus 1. Now from these two we take the k plus 1 as a common, then in bracket we will get k plus 2. Therefore this is RHS and hence LHS is equals to RHS. Therefore the last step is now step number 4. Therefore the given result is true for p of k plus 1 is a 2. In this case, we for step number 1 and step number 3, we prove that LHS is equals to RHS, and step number 2 is only for the assumption. That is, in that step we replace n by k. Now induction is we generalize the result here. That is, from all the above step by the principle of mathematical induction, the result p of n is a true for all small n belongs to capital N, and hence we generalize the statement. We write the final result, that is the 2 plus 4 plus 6 now the second problem. That is 3 plus 7 plus 11 plus dash dash plus 2 up to n terms, n in bracket to n plus 1. Now the step number 1, and it is called the foundation. That is 3 plus 4 plus 7 to the n term, and is equals to n in bracket to n plus 1. Now see this here, the n term is not given, but though it is not given, we can construct that n term. That is, we have learned the arithmetic progression. That is, the last term is not there. Now we can form this last term. Now here a is equals to 3, d is equals to 4. If we say this, the given sequence is in AP. Now Tn is equals to a plus n minus 1 into d. Now see this here, the value of a is 3, d is 4. If you calculate it, then you will get 3 plus 4n minus 4. That is a 4n minus 1 will be the nth term. 3 plus 4n minus 4, that is 4n minus 1. This is the Tn. That is, we do not have the last nth term, therefore we calculate by using the arithmetic progression. We see this, what type of the sequence is there. Therefore now An is equals to 3 plus 7 plus 11 plus dash dash plus in bracket 4n minus 1 is equals to n in bracket 2n plus 1. Now when n is equals to 1, now see this LHS, there is only the first term. When n is equals to 1, what is there? LHS is 3. Now we'll consider for the RHS. What is RHS? The RHS is n in bracket 2n plus 1. Therefore, in this step, we substitute n is equals to 1 and calculate. If it is 3, then we say that LHS is equals to RHS. It means that our first step is here. Now see this RHS. N in bracket 2n plus 1, that is a 1 in bracket 2n plus 1 plus 1, that is a 2 plus 1, that is equals to 3. This is number 2. And therefore from 1 and 2, LHS is equals to RHS. Now the step number 2. And this step is called assumption. It is called the assumptions because we assume here. Assume that let P of K is true. Therefore, P of K is true. That is, a K belongs to set of natural number 3 plus 7 plus 11 plus 4k minus 1 is equals to k in bracket 2k plus 1. This is 1. Now we will prove that it is true for P of K plus 1 is true. That is 3 plus 7 plus 11 and 4k minus 1. Again, what is our next step? This k is replaced by k plus 1. Then you will get 4k plus 4 minus 1, that is a 3. This is important. That is, here we replace k by k plus 1. Now see this again here. This k is replaced by k plus 1. That is 4k plus 4, but here is minus 1. Therefore, the next term is a 4k plus 3 equal to in bracket k plus 1 and 2k plus 3. I underlined it. That is a D. Now consider the LHS of this term. This is important. This step is called the succession. That is a step number 3. And in this step, there are the calculation. Now see this 3 plus 7 plus 11 plus 4k minus 1. For the values of all these values are k in bracket 2k plus 1 plus 4k plus 3. And if you calculate it, then you will get 2k square plus k plus 4k plus 3. That is a 2k square plus 5k plus 3. Therefore, that is, you can factorize this. The product is 6 and normal factorization for the quadratic equation k in bracket 2k plus 3 plus 1 in bracket 2k plus 3. That is a 2k plus 3. And in next bracket you will get k plus 1. Therefore, LHS is equals to RHS, and hence we generalize result in the step number 4. That is a P of K plus 1 is a true. This is the step number 4 now. That is induction, that is we generalize the result. Therefore, by the principle of same dialogues are there. Therefore, by the principle of mathematical induction, by the principle of mathematical induction, the result P of n is true for all small n belongs to capital N. Hence, 3 plus 7 plus 11 plus dash dash plus 2 n term is equals to n in bracket 2n plus 1, and hence the result is proved. Now, see these steps. These examples are big one. If you see this in small letters, they are like this. Next example. Example number 3. Plus 2 square plus 3 square plus dash dash plus n square is equals to n in bracket n plus 1 into 2 plus 1 upon 6. This type of the result that I have seen in the sequence. Now the step number 1. This is the foundation. Number 1 is very easy. The given result 2 power n is equals to 1. That is P of n is equal to 1 square plus 2 square plus 3 square plus n square n in bracket 1 into 2 upon 6. For small n belongs to the capital N. That is LHS is equals to 1 square. That is, and RHS is equals to n into n plus 1 to n plus 1. We replace n by 1 and make the simple calculations are here. That is it. 6 upon 6, that is equals to LHS is equals to RHS. Therefore, the foundation is clear here. The first step is clear. Therefore, P of 1 is true. Now, the step number 2. Now for the second step. Let us assume that for some k belongs to set of natural number, P of k is true. Therefore, 1 square plus 2 square plus 3 square plus k square is equals to k in bracket k plus 1 into 2k plus 1 upon 6. This is our assumption. This is the second step is always for the assumption. First step is for the foundation. Now we will prove that P of k plus 1 is true. That is, to prove that 1 square plus 2 square plus 3 square plus 4 square dash dash plus k square, and next is a k plus 1 bracket square, and here on the right hand side k is replaced by k plus 1. This is the important step. K is replaced by k plus 1. Now see this here. In the step 1 we replace k by k plus 1 to the right hand side. Now see this here. This k is replaced by k plus 1. This k is replaced by k plus 1. It becomes k plus 2. And this k is also replaced by 2 in bracket k plus 1 upon 6. Therefore k plus 1, k plus 2, 2k plus 2 plus 1, that is a 6, 2 plus 1, that is a 3. Now this is important. Now we will consider, this is called the succession step. So the step number 3. Consider the LHS, that is a 1 square plus 2 square plus 3 square plus k square in bracket k plus 1 in bracket square, and the value of this is k in bracket k plus 1, that is a 2k plus 1 upon 6 plus k plus 1 bracket square. Therefore, from the result 1, now we will take the k plus 1 as a common. Simplify this. K plus 1 as common. Then what is in bracket? K in bracket 2k plus 1 upon 6. These two will remain here. Plus k plus 1. Not bracket square, it is a single power. Now simplify this. Then you will get k plus 1 multiplied with the 6. That is a k in bracket 2k plus 1 plus 6 in bracket k plus 1. Now this is the simplification. You can see this here. Okay. Next step. Therefore, the 2k square plus k plus 6k plus 6 upon 6. Now k plus 1, 2k square plus 7k plus 6. Now factorize it. 2k square plus 6, that is a 12, and 3 plus 4, that is a 7, and their product is also 12. These are the factors. Therefore, k plus 1 in bracket, we take the 2k in bracket k plus 2, 3 in bracket k plus 2 upon 6. Therefore, k plus 1 in bracket k plus 2 in bracket 2k plus 3 upon 6. This is the RHS. Therefore, LHS is equals to RHS. Therefore, P of k plus 1 is true. And then now, next step. That is step number 4. That is induction. In this step, we generalize the result by the principle of mathematical induction. The result P of n is true for all n belongs to capital N. Hence, 1 square plus 2 square plus 3 square dash up to the n square, that is equals to n in bracket n plus 1 to n plus 1 upon 6. Small n belongs to the capital N. Now the next example number 4. 1 square plus 3 square plus 5 square plus 2n minus 1 bracket square is equals to n upon 3 2n minus 1 into 2n plus 1. Here the last term we have given here. Now here we will write, let the p of n is equals to 1 square plus 3 square plus 5 square plus 2n minus 1 bracket square n upon 3 2n minus 1 into 2n plus 1. Step number 1, that is the foundation. Given result is true for n is equals to 1. Every time these are the same steps for all the examples. This is the foundation. To prove n is equals to 1, it is true. What is that LHS? That is a 1 square problem. It's treated as the first term, and in RHS we substitute n is equals to 1 and we get the result. For the LHS, first term is 1 square, that is equals to 1, and for RHS, n upon 3 2n minus 1 2n plus 1, we substitute here n is equals to 1 and we get the result. That is RHS is 1 by 3, 2 into 1 minus 1, 2n, 2 into 1 plus 1, that is 1 by 3, and overall we are getting 1, which is the RHS. That is, therefore LHS is equals to RHS. Therefore, the next step, assumption. That is a step number 2. The given result is true for n is equals to k. Assume that here we will prove that given result is true for n is equals to k. Now the assumptions. Here we will prove that the given result is true for n is equals to k. That is 1 square plus 3 square plus 5 square plus dash dash 2k minus 1 bracket square is equals to k upon 3 2k minus 1 into 2k plus 1. Here we only replace n by k. Now this step is again very important. That is, here we prove the above result is true for n is equals to k plus 1. Therefore, 1 square plus 3 square plus 5 square plus dash dash plus 2k minus 1, because we want to write the next term. What is that here? There is a k is replaced by k plus 1. That is a 2 in bracket. K plus 1 minus 1 bracket square is equals to k plus 1 upon 3 into 2 in bracket k plus 1 minus 1, 2 in bracket k plus 1 plus 1. Therefore, k plus 1 upon 3, 2k plus 1, 2k plus 3. Therefore, k plus 1, 2k plus 1, 2k plus 3 upon 3. Now consider LHS. Consider the LHS. Now we write here LHS. Now the values of these terms, that is underlined term, that we know from the above equation number 1. That is, its value is k upon 3, 2k minus 1 into 2k plus 1. And what is the next? 2k plus 1 bracket square. Now simplify this again. This simplification is simple. That is a k in bracket 2k minus 1 into 2k plus 1 plus 3 into 2k plus 1 bracket square upon 3. Now take 2k plus 1 as a common, then in bracket you will get k in bracket 2k minus 1 plus 3 in bracket 2k plus 1 bracket complete, and this whole divided by 3, that is a 2k square minus k plus 6k plus 3 upon 6, upon 3. Now simplify this, that is a 2k plus 1, 2k square plus 5k plus 3, normal simplification is there, divided by 3. This is a 2k plus 1. Now factorize this, 2k square plus 2k plus 3k plus 3. Now underline 2k plus 1. Take the 2k common, then in bracket you will get k plus 1 plus 3 in bracket k plus 1 upon 3. Take the common. This is simplification. It's normal simplification, that is, here we factorize k plus 1 is common, then 2k plus 3, 2k plus 1, and in this way. Therefore, their values are, now we'll substitute here. That is equals to RHS. This is LHS is equals to RHS. Now the next is, that is the induction, step number 4. That is, here we generalize the result. From all above, by the principle of mathematical induction, by the principle of mathematical induction, P of n is a true for small n belongs to capital N. Hence, 1 square plus 3 square plus 5 square plus 2n minus 1 bracket square is equals to n upon 3 in bracket 2n minus 1, 2n plus 1. Hence the result. Now next is question number 5. That is a 1 cube plus 3 cube plus 5 cube plus dash dash to the n term that is equals to n square in bracket 2n square minus 1 now here we do not have the last term here, therefore we'll calculate it. Let Pn is equals to 1 cube plus 3 cube plus 5 cube dash to the nth term, then n square in bracket 2n square minus 1 for all n belongs to capital N. This is the step 1 now. That is, before that step 1 we will calculate the last term. Last term of the RHS not given. Therefore, these are the 1, 3, 5 and they are in AP. First term is a common difference is d is equals to 2. Therefore, the nth term, that is the Tn is equals to a plus n minus 1 into d. A is 1, n minus 1, d is 2. That is a 1 in 2n minus 2, 2n minus 1. Therefore, the nth term of the series that is the last term is 2n minus 1 bracket cube. Therefore, P of n now, that is 1 cube plus 3 cube plus 5 cube plus dash dash plus 2n minus 1 bracket cube is equals to n square in bracket 2n square minus 1 now the step number 1 and it is the foundation. Now in this step we prove the result for n is equals to 1. Now here the first term is 1, put n is equals to 1, it is a 1 cube, and for this RHS that is a 1, 2 into 1 minus 1, overall it is again 1. Therefore LHS is equals to RHS. Now here but 1 cube is 1 and the RHS. N square in bracket 2n square minus 1, 1 square, that is a 2, 1 square minus 1. Therefore 1, 2 minus 1, that is 1. This is number 2. Therefore LHS is equals to RHS from 1 and 2. Now the step number 2, which is the assumption, that is a given result is true for n is equals to k. Let us assume that for some small k belongs to the set of natural number, p of k is a true. That is 1 cube plus 3 cube plus 5 cube plus dash dash plus 2 k minus 1 bracket cube is equals to n is replaced by k here, that is a k square in bracket 2k square minus 1. This is the one, equation number 1, that is the step number 1. Equation 1 we treat here. Then to prove that, this is the step number 3, that is called the succession. P of k plus 1 is true. That is, to prove that, here we replace k by k plus 1 and we get the last term. So see this. How this term is come here. Now here k is replaced by k plus 1. If we replace this k by k plus 1, then in bracket you will get 2k plus 2, and here is minus 1. Plus 2 minus 1 becomes plus 1. And on the right hand side, only replacement is there. That is, the k is replaced by k plus 1. That is a k plus 1 bracket square. In bracket, two in bracket k plus 1 bracket square means what? K square plus 2k plus 1 minus 1. That is a k plus 1 bracket square, 2k square plus 4k plus 2 minus 1, and solve that. K plus 1 bracket square, 2k square plus 4k plus 1 . It is in the step number 2. Now consider LHS. That is a 1 cube plus 3 cube plus 5 cube plus 2k minus 1 bracket cube plus 2k plus 1 bracket cube. Now the value of this is from the 1, that is, we have substituted it. It is a k square in bracket 2k square minus 1 plus 2k plus 1 bracket cube. Now evaluate this, then you will get the, if we evaluate this, that is a 2k raised to 4 minus k square plus 8k cube plus 3 in bracket 2k square, that is k square into 1 plus, again the expansion of a plus b bracket cube, you can expand it. That is a 2k raised to 4 plus 8 cube as it is. Now the next is here 12k square minus k square plus 6k plus 1. Simplify this, 2k raised to 4 plus 8k cube plus 11k square plus 6k plus 1. Now we want the result that is equals to the RHS. That is a 2k raised to 4 can be written as 4k cube plus 2k square plus 4k cube. Now this is only the adjustment of the terms here according to the RHS. Therefore we adjust here, that is a 2k raised to 4 as it is. This 8k cube can be written as 4k cube. Again 11k square can be written as 2k square. Next is, what is the remaining here? The remaining here is a 4k cube, 9k square plus 6k plus 1. Therefore now take the common from these, that is a take 2k square as a common, then in bracket k square plus 2k plus 1. From the next, we again adjustment of the terms, that is a 4k cube plus 8k square plus 4k. Again we can take the common from this. Then and then you will get again k square plus 2k plus 1, and the last is like this, k square plus 2k plus 1. Now overall, that is it. If we take the common, in bracket you will get the same terms, and from the last you can take the 1 as common, that is the k square plus 2k plus 1. Now from all these terms you can take the k square plus 2k plus 1 as a common, and in the bracket you will get 2k square plus 4k plus 1. Therefore this is the RHS, and hence LHS is equals to RHS. Therefore P of k plus 1 is true. P of k plus 1 is true here. Now the step number 4. This is the induction. We write here only by the principle of mathematical induction. Given result is true for small n belongs to the capital N, and whatever that question given, we write here last step. By the principle of mathematical induction, P of n is true for small n belongs to the capital N. That is 1 cube plus 3 cube plus 5 cube to the nth term, and that is equals to n square in bracket 2n square minus 1 for all n belongs to. Question number 6, that is a 1.2 plus 2.3 plus 3.4 plus dash dash plus n in bracket n plus 1 is equals to n upon 3 in bracket n plus 1 n plus 2. Now let here P of n is equals to 1.2 plus 2.3 plus 3.4 plus dash dash plus n in bracket n plus 1 is equals to n upon 3 into n plus 1 n plus 2. For all small n belongs to capital N, this is the step number 1, that is called the foundation. That is to prove P of n is true for n is equals to 1. Therefore here LHS is equals to 1.2, that is equals to 2. This is 1, and the RHS, that is equals to 1 upon 3. We substitute in the formula, n is equals to 1 here. That is n upon 3 in bracket n plus 1 to n upon 3 n plus 1 n plus 2. N is replaced by 1, and after the calculation you are getting the 2 here. This is RHS. Therefore from 1 and 2, LHS is equals to RHS. And that is the P of n is true for n is equals to 1. Now the step number 2, which is the assumption. Let assume that P of k is true P of k is true that is a 1.2 plus 2.3 plus 3.4 plus dash dash plus k in bracket k plus 1 is equals to k upon 3 in bracket k plus 1 into k plus 2. This is the one. Now the step number 2, that is called the succession. To prove that p of k plus 1 is true, therefore here again the k is replaced by k plus 1, that is here k is replaced by k plus 1, then you will get k plus 1 and k plus 2. And also here we replace by k plus 1. Now see this result, that is a k plus 1, this is the previous term, and the next term is a k plus 1, k plus 1 plus 1. Again here is a k plus 1 upon 3, k plus 1 plus 1, k plus 1 plus 2. And again write one more step, that is a k plus 1 upon 3, k plus 2 and the k plus 3. Now see this again, we write here 1.2 plus 2.3 plus 2.4, and in this way k in bracket k plus 1, k plus 1, k plus 2. Now consider next, that is the LHS of this equation. Now LHS 1.2 plus 2.3 plus 3.4 plus dash dash k in bracket k plus 1, k plus 1 into k plus 2. Here k in bracket k plus 1. We substitute the value. What is that? K upon 3 in bracket k plus 1 we are writing that. We have substituted here, that is a k upon 3. Now see this here. We have substituted the value, the underline. Had underline here. What is the value of this? K upon 3 into k plus 1 into k plus 2. Add this term, next term, and simplify this. Then you will get, that is a k plus 1, k plus 2. We take the common, that is the k plus 1 and k plus 2 common here. Here is a k plus 1 and k plus 2. Here is also k plus 1. If you take the k plus 1, k plus 2 common, then in bracket you will get k upon 3 plus 1 bracket complete. Now simplify this. That is a k plus 1, k plus 2, k plus 3 whole divided by 3. Therefore, this is the RHS. Therefore, LHS is equals to RHS. Therefore, the P of n is true for n is equals to k plus 1. This is the next step number 4. That is the induction. By the principle of mathematical induction, we always write this dialog for the last step, that is the fourth step. What is that? By the principle of mathematical induction, the result P of n is true for all n belongs to capital N. 1.2 plus 2.3 plus 3.4 plus dash dash 2 plus n in bracket n plus 1 is equals to n upon 3, n plus 1, n plus 2. And here's the result. Now the question number 6. Now the next example is 1.2 plus 2.3 plus 5.7 up to the nth term is equals to n upon 3, 4n square plus 6n minus 1. Yeah. Let p of n is equals to 1.3 plus 3.5 plus 5.7 plus dash dash to the nth term is equals to n upon 3. 4n square plus 6n minus 1 for all n belongs to the capital N. Now we'll find out here the nth term is not there and the given sequence series is the product of the two terms. Therefore, we'll find out the independently Tn for these two terms. Now the first term in the series is, that is 1, 3, 5. Therefore here A is equals to 1, D is equals to 2. Therefore it is an AP. Let's say Tn is A plus n minus 1 into D. This way I have done sequence and series. Therefore the nth term for the first term is 2n minus 1. Also second term, that is a 3, 5, 7. A is equals to 3, D is equals to 2. Nth term, it is in AP. Nth term is equals to A plus n minus 1 into D. That is 3 plus 2n minus 2 and 2n plus 1. And therefore, this is the second term. Therefore, the nth term of the series is 2n minus 1 into 2n plus 1. Therefore, P of n is equals to 1.3 plus 3.5 plus 5.7 plus dash dash up to the 2n minus 1 into 2n plus 1 is equals to n upon 3, 4n square plus 6n minus 1. Now, the first step now, that is the foundation. The given result is true for n is equals to 1. That is the foundation. To prove that P of 1 is true or n is equals to 1, LHS is equals to 1.3, the first term, and that is equals to 3. Now the RHS, n upon 3 in bracket 4n square plus 6n minus 1. Put n is equals to 1, that is 1 upon 3. 4 plus 6 minus 1, that is equals to 1 upon 3. 4 plus 6 minus 1, that is 1 by 3. And which is 9. 1 upon 3 into 9, that is equals to 3. This is number 2. Therefore, from 1 and 2, LHS is equals to RHS. Therefore, the P of 1 is true. Second step is succession. Second step is it is the assumption. We assume that here the given result is true for n is equals to k. Second step is assumption. P of k is true. That is n is replaced by only k. 1.3 plus 3.5 plus 5.7 plus dash dash 2k minus 1, 2k plus 1. For every problem, same dialogues are there. These are the k upon 3, 4k square plus 6k minus 1. This is 1. Now the step number 3 here, that is for the succession. To prove the result that p of k plus 1 is true, that is to prove that 1.3 plus 3.5 plus 5.7 plus dash dash plus 2k minus 1 into 2k plus 1 is equals to, plus. Here again the k is replaced by k plus 1. Now see this here. This k is replaced by k plus 1. Therefore it is a 2k, 2 in bracket k plus 1 minus 1. And here is also this k is replaced by k plus 1. Now see this simplification. That is a 2 in bracket k plus 1 plus 1. That is now the RHS. K plus 1 upon 3 in bracket 4 in bracket k plus 1 bracket square plus 6 in bracket k plus 1 minus 1. Now consider LHS 1.3 plus 3.5 plus 5.7 plus dash dash 2k minus 1 and 2k plus 1 plus 2k plus 1 in first bracket two k plus 3 now substitute the value k upon 3 in bracket 4k square plus 6k minus 1 plus 2k plus 1 2k plus 3 which is the from 1. Now simplify here. This simplification is important. That is k in bracket 4k square plus 6k minus 1 plus 3 in bracket 2k plus 1 2k plus 3 upon 3, that is 1 upon 3. Now simplification is 4k cube plus 6k minus k plus 3 in bracket 2k. Now there, this is the product. This 2k into 2k, 2k square, 6k plus 2k plus 3. That is equals to 1 by 3. Now the product of the 4k cube plus 6k square minus k plus 12k square. Multiplication of this carried out. 12k plus 9. That is equals to 1 upon 3 4k cube plus 18k square plus 23k plus 9 Now simplify this. That is 1 by 3. 4k cube plus 4k square plus 14k square plus 23k plus 9. Take the common. 4k square plus k plus 1. Now from these two, again 14k square plus 14k plus 9k plus 9. 1 by 3. 4k square k plus 1. 14k in bracket k plus 1. 9 in bracket k plus 1. Take the k plus 1 as a common. 1 by 3 in bracket k plus 1. Then in bracket you will get 4k square plus 14k plus 9. Bracket complete. Therefore, now what type of the terms we require, that we will arrange here now. That is 1 by 3 in bracket 4k square plus, we can take the common, that is 8k plus 4. Now what are the remaining terms? The remaining terms are 6k plus 5. That is, remaining is 5. We adjust here, that is a 6 minus 1. It becomes 5. Now see this again step. That is a 4k square plus 14k can be written as 8k plus 6k, that is 14k. 9 can be written as 4 plus 6 minus 1, that is a 10 minus 1. We require the like this. Now the next is that is a 4 in bracket k square plus 2k plus 1 plus 6 in bracket k plus 1 minus 1. Now 1 by 3 k plus 1 in bracket 4 k plus 1 bracket square plus 6 in bracket k plus 1 minus 1. That is equals to RHS, and hence LHS is equals to RHS. That is a P of k plus 1 is true. Now the step number 4th. Therefore, by induction, by the principle of mathematical induction, the given result is true for small n belongs to the capital N. P of n is true for all small n belongs to capital N, that is 1.3 plus 3.5 plus 5.7 plus dash dash to the nth term, and that is equals to n upon 3 in bracket 4n square plus 6n minus 1. Now the example number 8, that is 1 upon 1.3 plus 1 upon 3.5 plus 1 upon 5.7 plus dash dash 1 upon 2n minus 1 to n plus 1 is equals to n upon 2n plus 1. Let P of n is equals to first assumption, that is we consider here the given result is, for every example we write this step for all n small n belongs to the capital N. Now the step number 1, that is the foundation. For n is equals to LHS is equals to 1 upon 1.3, that is equals to 1 by 3, this is 1. RHS is equals to n upon 2n plus 1, that is a 1 upon 2 into 1 plus 1, that is 1 by 3. This is number 2. Therefore, from 1 and 2, LHS is equals to RHS. Now the step number 2. This is the assumption. Let us assume that the given result is true for n is equals to k. That is, small k belongs to the capital N, that is the p of k is a true. That is 1 upon 1.3 plus 1 upon 3.5 plus 1 upon 5.7 plus dash dash plus 1 upon 2k minus 1 upon into 2k plus 1, that is equals to k upon 2k plus 1. This is 1. Now the next is, then to prove that is a succession. The given result is true for n is equals to k plus 1. Prove that p of k plus 1 is a true. That is to prove that 1 upon 1.3 plus 1 upon 3.5 plus 1 upon 5.7 plus dash dash plus 1 upon 2k minus 1, 2k plus 1 plus 1 upon, here k is replaced by k plus 1, then we will get the result. Here k is replaced by k plus 1, then you will get 2k plus 1. Here again k is replaced by k plus 1, then you will get 2k plus 2 plus 1, that is a 3. And next is a k plus 1 upon 2k plus 3. Now therefore LHS 1 upon 1.3 plus 1 upon 3.5 plus 1 upon 5.7 plus dash dash plus 1 upon 2k minus 1 into 2k plus 1 plus 1 upon 2k plus 1 into 2k plus 3. Now the sum of these, that is from the one you will get that is k upon 2k plus 1 plus 1 upon 2k plus 1, 2k plus 3. Now simplify here. Now we will simplify, that is 1 upon 2k plus 1, take the common, then here you will get k plus 1 upon 2k plus 3, that is 1 upon 2k plus 1, 2k square plus 3k plus 1 upon 2k plus 3. Therefore 1 upon 2k plus 1, 2k square plus 2k plus k plus 1 upon 2k plus 3. Therefore the result is, now factorize this. That's very simple factors, 2k plus 1 into k plus 1. Now here 2k plus 1, 2k plus 1 get cancelled, and to the denominator 2k plus 3, 2k plus 3, these 2 get cancelled, and it is a k plus 1 upon 2k plus 3. That is equals to RHS. Therefore the p of k plus 1 is true. Now the step number 4, this is the induction. Here we write only the dialog. The given result is true for n small n belongs to the capital N, and hence the result. That is, by the principle of mathematical induction, Try the principle of mathematical induction. P of n is a true for all small n belongs to the capital N. 1 upon 1.3 plus 1 upon 3.5 plus 1 upon 5.7 plus dash dash plus 1 upon 2n minus 1 into 2n plus 1 is equals to n upon 2n plus 1. Now the next is example number 9. Now the next example is 1 upon 3.5 plus 1 upon 5.7, that is multiplication 1 upon 7.9 plus dash dash to the n term, that is equals to n upon 2n plus 3. Now the first step, let P of n is equals to 1 upon 3.5 plus 5.7 plus 7 plus 1 upon 7.9 plus 2 dash dash n term, that is n upon 3 in bracket 2n plus 3. For small n belongs to the capital N, now we will find the nth term. First, that is last term, nth term is not given there. 3, 5, 7. 3, 5, 7, a is equals to 3, d is equals to 2, then we tn is equals to a plus n minus 1 into t, and we get the first term, that is a 2n plus 1. Now for the second term, 5, 7, 9, a is equals to 5, d is equals to 2, then tn is equals to a plus n minus 1 into d, that is 5 plus n minus 1, d is 2. Simplify this, that is a 2n plus 3. Therefore, nth term of series in LHS of Pn is equals to 1 upon 2n plus 1 into 2n plus 3. This is the nth term. Therefore, the P of n is equals to 1 upon 3.5 plus 1 upon 5.7 plus 1 upon 7.9 plus dash dash plus 1 upon 2n plus 1 into 2n plus 3, that is equals to n upon in bracket n upon 3 in bracket 2n plus 3. Now we'll prove this. Now the first is, that is a foundation. Given result is true for n is equals to 1. Therefore, to prove P of n is true for n is equals to 1, therefore we consider the LHS. And what is the term? First term of the LHS, that is a 1 upon 3.5, that is equals to 1 upon, or we may write 1 upon 15 also, but keep it as it is. Now consider the RHS. Now see this formula and substitute, that is n is equals to 1, and after simplification you will get, that is 1 upon 3.5. Therefore from 1 and 2, LHS is equals to RHS. Now the step number 2, which is the assumption, that is the given result is true for n is equals to k. Here we replace only the n is equals to k and write it as equation 1. Let us assume that for small k belongs to the capital N, P of k is a true. That is 1 upon 3.5 plus 1 upon 5.7 plus 1 upon 7.9 dash dash plus 1 upon 2k plus 1 into 2k plus 3. That is equals to k upon 3 in bracket 2k plus 3. Now this is the question 1. Now the succession, this is the important step. That is we'll prove here the given result is true for n is equals to k plus 1. To prove that p of k plus 1 is true, that is 1 upon 3.5, 1 upon 5.7, 1 upon 7.9 plus dash dash plus 1 upon. Here is a k is replaced by k plus 1. This is the first term. And what will be the next term? That is a k is replaced by, that is a 2k plus 3. Here k is replaced by k plus 1. Then you will get 2k plus 3. Now see this again. How it comes. Here k is replaced by k plus 1. Then you will get 2k plus 3. K is replaced by k plus 1. That is a 2k plus 2. That is 5. That is a 2k plus 5. Therefore, k plus 1 upon 3 in bracket 2k plus 5. This is the third. Now the LHS is equals to 1 upon 3.5 plus 1 upon 5.7 plus 1 upon 7.9 plus 1 upon 2k plus 1, 2k plus 3 plus 1 upon 2k plus 3, 2k plus 5. Now see these the terms. That is k upon 3 in bracket 2k plus 3 plus 1 upon 2k plus 3, 2k plus 5. Take 1 upon 2k plus 3 as a common. Therefore 1 upon 2k plus 3, k by 3 plus 1 upon 2k plus 5, 1 upon 2k plus 3, and now simplify this. That is k into 2k plus 5. Then you will get 2k square plus 5k and cross multiplication plus 3 upon the multiplication of these two terms denominator. That is a 3 in bracket 2k plus 5. Therefore 1 upon 3 in bracket 2k plus 3, 2k plus 5. That is 2k square plus 2k plus 3k. Now factorize this. That is 1 upon 3 in bracket 2k plus 3, 2k plus 5, and after factorization you will get, that is a 2k, k plus 1 plus 3 in bracket k plus 1. That is a k plus 1 in one bracket, 2k plus 3 in another bracket, upon 3 in bracket 2k plus 3, 2k plus 5, 2k plus 3, 2k plus 3 get cancel, and you will get k plus 1 upon 3 in bracket 2k plus 5. Therefore this is the RHS, and hence LHS is equals to RHS. Therefore the P of k plus 1 is true. Now the step number 4, which is the induction. That is, in this step we conclude the result. Therefore, by the principle of the mathematical induction, the given result is true for small n belongs to the capital N, and we write the whatever the question given. By the mathematical principle of mathematical induction, the result P of n is true for all small n belongs to the capital N. Therefore, 1 upon 3.5 plus 1 upon 5.7 plus 1 upon 7.9 plus dash dash 2, the n term, and that is equals to n upon 3 in bracket 2n plus, and in this way I had concluded. I was concluding here, but I'm again continue here. I was making the two parts for this video, but afterward I decide that I will continue the example. This is the big video. Now the next, these are the different types of the example. That is example number 10. That is a 2 raised to 3n minus 1 is divisible by 7. That is here 2 raised to 3n minus 1 is divisible by 7 if only if and only if 2 raised to 3n minus 1 is multiple of 7. This is the first. That is 2 raised to 7 minus 1 must be multiple of the 7. Let p of n, we assume that is a 2 raised to 3n minus 1. Therefore, that is equals to, what is the value of this? That is a 2 raised to 3n minus 1 is equals to 7n, where small n belongs to the capital N. Now the step number 1. This. Let n is equals to 1. The given result is 2 for n is equals to 1. Then what is that? Is a 2 raised to 3n minus 1. Now if we replace n is equals to 1, then you will get 2 raised to 3 minus 1, that is 8 minus 1, that is equals to 7, is equals to 7 into 1, that is a 2 raised to 3n minus 1 is multiple of 7. And hence the p of 1 is a 2. Now the step number 2, let p of k is true for assumption step here. P of k is true for n is equals to k, that is a 2 raised to 3k minus 1 is equals to 7a, where a belongs to the set of natural number. Now the step number 3, that is a 2 raised to 3k minus 1 is equals to 7a plus 1. This is the number 1. Equation 1. Now the next step, the given result is true for n is equals to k plus 1. Now we have to prove that p of k plus 1 is true. This is the succession. P of k plus 1 is true. To prove that two raised to 3k plus 1 minus 1 is multiple of 7, that is 2 raised to 3k plus 3 minus 1 is a multiple of, that is equals to 7b. Suppose where b belongs to set of natural number, therefore 2 raised to 3k plus 3 minus 1 is equals to, it can be written as like this, 2 raised to 3k dot 2 raised to 3 minus 1 that is equals to, we substitute the value. What is its a value? That is a 2 raised to 3k value is a 7a plus 1. 2 raised to 3 is 8 here. we substitute here value of the 2k, which is a 7a plus 1 from 1 into 2 raised to 3 is 8 minus 1. And if we evaluate this, then what will happen? This is a 7a into 8 plus 7. Take 7 as a common. And overall it is a multiple of the 7. That is a 7 in bracket 8a plus 1. Therefore it is a 7 8a plus 1, that is a b, where b is equals to 8a plus 1, which belongs to set of natural numbers. That we have defined this b also in previous step. That is a, therefore p of k plus 1 is true. Now the step number 4, let's say induction step. Therefore, by the principle of mathematical induction, by the principle of n is true for all small n belongs to the capital N, that is a 2 raised to 3n minus 1 is divisible by 7, and hence the result for all small n belongs to capital N. Now the example number 11. Now the example number 11. 2 raised to 4n minus 1 is divisible by 15. Two raised to 4n minus 1 is divisible by 15 if and only if 2 raised to 4n minus 1 is multiple of 15. Same dialogues are here again there. Now let Pn is equals to 2 raised to 4n minus 1 is equals to 15m, where m belongs to set of natural number. Now here again the step number 1. Therefore, for n is equals to 1, two raised to 4n minus 1 is equals to 2 raised to 4 into 1 minus 1, that is a 2 raised to 4 minus 1. 16 minus 1, that is equals to 15, which is divisible by 15. Therefore, P of 1 is true. Step number 2. That is the assumption. The first was foundation. Second is assumption. Assume that the P of k is true. That is 2 raised to 4k minus 1 is equals to 15 a, where a belongs to set of natural number. 2 raised to 4k is equals to 15a plus 1. This is the one. To prove that P of k plus 1 is true, 2 raised to 4k plus 1 minus 1 is 2 raised to 4 in bracket k plus 1 minus 1 is a multiple of 15. Now see this here is multiple of 15, that is a 2 raised to 4 in bracket k plus 1 minus 1 is equals to 15b, where small b belongs to capital N. Now 2 raised to 4k plus 4 minus 1 is equals to we split up it, that is a 2 raised to 4k dot 2 raised to 4 minus 1. We can write in this manner. That is a 2 raised to 4k, 16 minus 1. And what is the value of 2 raised to 4k? Its a value is a 15a plus 1 into the 16 minus 1. And if we evaluate this, take the 15 as a common, then you will get 16a plus 1. That is b, where b is equals to 16a plus 1 and it belongs to the set of natural number. Therefore, p of k plus 1 is true. Now the step number 4. By the principle of mathematical induction, p of n is true for all small n belongs to capital N. This is the induction, and therefore 2 raised to 4n minus 1 is divisible by 15. Now the next example number 12. 3 raised to 2, 3 raised to n minus 2n minus 1 is divisible by 4. That is a 3 raised to n minus 2n minus 1 is divisible by 4 if and only if 3 raised to n minus 2n minus 1 is multiple of 4. Let p of n is equals to 3 raised to n minus 2n minus 1 is equals to 4n, where small m belongs to capital N. Now the step number 1, for n is equals to 1, 3 raised to n minus 2n minus 1 is equals to, if we substitute n is equals to 1, that is a 3, minus 2 into 1 minus 1, that is equals to 0, which is divisible by 4. Therefore, p of 1 is true. Now for the second, which is the assumption step. Let us assume that for some small k belongs to capital N, p of k is true. that is 3 raised to k minus 2k minus 1 is equals to 4a, where a small a belongs to capital N. Therefore, 3 raised to k is equals to 4a plus 2k plus 1. This is the one. Now the step number 3. Which is the succession. To prove that p of k plus 1 is true, that is 3 raised to k plus 1 minus 2 in bracket k plus 1 minus 1 is multiple of 4, that is 3 raised to k plus 1 minus 2k minus 2 in bracket k plus 1 minus 1 is equals to 4b, where b belongs to the set of natural number. Is multiple of 4 means that is 3 raised to k plus 1 minus 2 in bracket k plus 1 minus 1 is equals to we evaluate this term, that is 3 raised to k plus 1 can be written as 3 raised to k into 3 minus 2k minus 2 minus 1, that is equals to, substitute the value. What is the value? The value of 3 raised to k. The value of 3 raised to k is a 4a plus 2k plus 1 into 3 minus 2k minus 3. That is a 12a plus 6k plus 3 minus 2k minus 3. That is a 12a plus 4k. Take 4 as common, then in bracket you will get 3a plus k, where b is equals to 3a plus k, and which belongs to the set of natural number. Therefore, p of k plus 1 is true. And now the induction passed. And hence, by the same dialogue is here again, by the principle of the mathematical induction. Principle of mathematical induction. P of n is true for all small n belongs to capital N, that is 3 raised to n minus 2n minus 1, is divisible by 4 for all small n belongs to capital N. Now the next example, example number 13. 5 plus 5 square plus 5 cube plus dash dash up to the 5 raised to n is equals to 5 by 4, 5 raised to n minus 1. Now let p of n is equals to 5 plus 5 square plus 5 raised to 3 plus dash dash 5 raised to n is equals to 5 by 4 in bracket 5 raised to n minus 1. Step 1, for small n is equals to 1, n belongs to the capital N. That is a LHS is equals to 5 and the RHS. We substitute here n is equals to 1, 5 by 4 in bracket 5 raised to n minus 1, 5 by 4, 5 raised to 1 minus 1, that is a 5 by 4 into 4, that is equals to 5. This is the RHS. This is number 2. Therefore, from 1 and 2, LHS is equals to RHS. Therefore, the steps 2. This is the assumption step. That is, let us assume that for some small k belongs to capital N, P of k is true. That is a 5 plus 5 square plus 5 raised to 3 plus dash dash 5 raised to n is equals to 5 by 4 in bracket 5 raised to k 5 by 4 in bracket 5 raised to k minus 1. This is 1. And now the step number 3. This is the succession. That is to prove that the given result is true for n is equals to k plus 1. Now in this case here 5 plus 5 square plus 5 raised to 3 plus 5 raised to k plus 5 raised to k plus 1 is equals to 5 by 4 in bracket 5 raised to k plus 1 minus 1. Now in this case consider LHS, that is the 5 plus 5 square plus same steps are here 5 raised to k plus 5 raised to k plus 1, that is 5 plus 5 square plus, and substitute here value. It's a value of 5 by 4 5 raised to k minus 1 plus 5 raised to k plus 1 on 3. Now evaluate this, that is a 5k multiplied here, that is a 4 into 5 raised to k plus 1. Now what is here? 5 raised to k plus 1 minus 5 plus 4 5 raised to k plus 1 upon 4. Take 5 raised to k plus 1 as a common. Therefore, you will get now see this step. What is here? That is 5. Here is a 5 raised to k plus 1, and here is a also the 5 raised to k plus 1. Now from this, now here is a 4 times and this is 1 times. It becomes a 5 raised to 5 into 5 raised to k plus 1. This is important step. This is 1 and this is 4. 1 plus 4 means what? 5. That is 5 into 5 raised to k plus 1. This is, and minus 4 is as it is. Okay. Therefore, from these two steps, what is you will get common from these two? Numerator is 5 and the denominator is a 4. That is 5 by 4 in bracket 5 raised to k plus 1 minus 1, and that is equals to RHS. Therefore, the P of k plus 1 is true. Therefore, by the principle of mathematical induction, P of n is true for small n belongs to the capital N. Therefore, 5 plus 5 square plus 5 raised to 3 plus dash dash plus 5 raised to n is equals to 5 by 4 in bracket 5 raised to n minus 1 for all small n belongs to capital N. Now the example number 15 or 14. Therefore, example number 14. Cos theta plus I times sin theta, Euler's theorem, plus cos of n theta plus I times sin of n theta. This we have learned in the first chapter, that is a complex number. Therefore, P of n is equals to cos of theta plus I times sin theta bracket raised to n is equals to cos of n theta plus I times sin of n theta For all small n belongs to capital N. This is the step 1. For small n is equals to 1. This is the first step. That is LHS is equals to cos of theta plus I times sin theta bracket raised to 1. And this is the n is equals to 1 as it is. Therefore, RHS is equals to cos of theta plus I times sin theta. That is, if we substitute n is equals to, now again, cos of n theta plus I times sin n theta. Now here we replace n is 1, cos of theta plus I times sin theta. This is 2. Therefore, from 1 and 2, LHS is equals to RHS. Now the step number 2. Let us assume that the given result is true for n is equals to k. For some small k belongs to the capital N is true. That is cos of theta plus I times sin theta. Bracket raised to k is equals to cos of k theta plus I times sin of k theta is equals to. This is treated as 1. This is the assumption. And now succession, that is the. Therefore, to prove that p of k plus 1 is a true, cos theta plus I times sin theta raised to k plus 1 is equals to cos of k plus 1 bracket complete into theta plus I times sin of k plus 1 bracket complete into theta. Now LHS cos of theta plus I times sin theta, that is equals to, that is a bracket raised to k plus 1, cos theta plus I times sin theta can be written as bracket raised to k cos of theta plus I times sin theta, that is equals to cos of k theta plus I times sin of k theta and cos of theta plus I times sin theta. This is the from 1. Therefore, now here is a product of the terms, that is a multiplication of the two brackets cos of k theta plus I times sin of k theta into in bracket cos theta plus I times sin theta. Normal multiplication of the bracket is here, cos of k theta into cos theta. This is here. Cos of k theta into I times sin theta. This is the normal multiplication is here, cos of k theta cos theta. Cos of k theta into I times sin of the system, I times sin of k theta into cos theta, I sin of k theta into I sin of theta. Now see this here, cos of k theta into cos theta minus, now here the I square is minus 1, therefore last term we consider here. These two terms are underlined terms. Now take I common from these two, second and third term, then in bracket you will get cos of k theta sin theta plus sin of k theta into cos theta. Now this is the expansion of cos of k plus k theta plus theta, and here is a sin of k theta plus theta. We take theta as a common, cos of k plus 1 theta plus I times sin of k plus 1 theta, and here is the RHS. Therefore, p of k plus 1 is true. Now the fourth step, by the principle of mathematical induction, P of n is true, for all small n belongs to capital N, therefore that is a cos theta plus I times sin theta bracket raised to n is equals to cos of n theta plus I times sin of n theta for small n belongs to capital N. Now the example number 15. That is a given that t n plus 1 is equals to 5tn plus 4. t1 is equals to 4, then prove that. Very interesting example this is. What is given? We have given that tn plus 1 is equals to 5, tn plus 4, t1 is 4. Prove by method of induction tn is equals to 5 raised to n minus 1. Now we have given this and we want to prove this. See this here. That the p of n is equals to tn 5 raised to n minus 1. This is the given. What is the given? Tn plus 1 is equals to 5 t raised tn plus t of n plus 1 is equals to 5 tn plus 4 and t1 is equals to 4. Now what is the step 1? Now see this. That is in the step 1. That is in this case here we'll prove n is equals to 1. Now for n is equals to 1, t of n plus 1 is equals to 5 tn plus 4. Now we substitute the value. That is t2 is equals to 5 t1 and we have the value of the t1 is 4. Therefore t2 is equals to 20 plus 4 and that is 24 and it is written as 25 minus 1 which is nothing but the t2 is equals to 5 raised to n minus 1. This is first. Therefore for n is equals to 1 the given result is true. Now for the step number 2, we will assume that the given result is true for n is equals to k. The result is true for n is equals to k. And we write here that is a p of k is equals to 5 raised to k. That is p of k is equals to t suffix n is equals to 5 raised to k minus 1 where we have given tk plus 1 is equals to 5 tk plus 4 and t1 is equals to 4. Now the step number 3, that is which is we call the succession. Now we'll prove that the given result is true for n is equals to k plus 1. Therefore t suffix n plus 1 is equals to 5 t suffix n plus 4. Now here replace n by k plus 1, then you will get t suffix k plus 1 is equals to 5 t suffix k plus 1 plus 4. That is a t suffix k plus 2 is equals to 5 t suffix k plus 1 plus 4. Therefore, now here we will substitute the value t of k plus 1 which is the 5tk plus 4. Here bracket complete. We substitute here t of k plus 1 and it is here. That is a 25tk plus 20 plus 4 and add it, you will get 24. But again, what is the value of this? It is a tk. Tk is a 5 raised to k minus 1. That is a 25 in bracket 5 raised to k minus 1 plus 24, and now this is the 25 dot 5 raised to k minus 25 plus 24. That is a 5 raised to 2, 5 raised to k minus 1. That is a 5 raised to k plus 2 minus 1. T suffix k plus 2 is equals to 5 raised to k plus 2 minus 1. Given result is true for p of k plus 2. Sorry, p of k plus 1. The given result is true for p of k plus 1. And hence, again, by the principle of mathematical induction, Tn is equals to 5 raised to n minus 1 is a true for Tn plus 1 is equals to 5 Tn plus 4 for T1 is equals to 4. And hence, proof. Now the problem number 16. Prove by method of induction. This is a simple question. It depends on the matrices. 1, 2, 0, 1. Matrix is equals to 1 plus 2n, 0, 1. For every small n belongs to the capital N. Now we have that is a p of n is equals to 1, 2, 0, 1 raised to n is equals to 1, 2, n, 0, 1 for all small n belongs to capital N. Now the step 1. Now we will prove given result is true for n is equals to 1. This is the foundation. That is bracket raised to n is as it is, and therefore 1, 2, 0, 1 and can be written as 1, 2 into 1, 0, 1 and which is RHS. Therefore LHS is equals to RHS. Step number 2. Now we will assume that the given result is true for n is equals to k. That is 1, 2, 0, 1. Bracket raised to k 1, 2, k, 0, 1, k. For small k belongs to capital N. And now the step number 3, which is the succession. Now we'll prove the result. It is true for n is equals to k plus 1. If you see all the example, I clear each and every, you will get the correct idea how to write. True for n is equals to k plus 1. Therefore 1, 2, 0, 1 and rest to k plus 1. That is a 1, 2 in bracket k plus 1, 0, 1. Therefore, now LHS is equals to, that is 1, 2 raised to k plus 1. That is 1, 2, 0, 1 raised to k into 1, 2, 0, 1 Therefore, we'll substitute the value. That is 1 plus 2k and 0, 1 from the result 1, 1, 2. Now the multiplication of the value. First row, first column. That is 1. 1 into 1 and 2k into 0. That is a 1. Now 1 into 2. That is a 2. And this is the 2 plus 2k. Next is 0 and 1. This is a matrix multiplication that we have cleared this chapter from the M1, and that's why that is a number 2, and therefore 1, 2 in bracket k plus 1, 0, 1, which is the RHS. And hence, that is a conclusion. By the principle of mathematical induction, for small n belongs to capital N, that is 1, 2, 0, 1 bracket is 2 n is equals to 1, 2 and 0, 1. And in this way, that is, we have completed the first exercise for the mathematical induction. Now we will see in the next video. Till then, goodbye. Now in this way, I had completed this exercise 4.1. I hope that you have understood all the problems, whatever that I had explained. Now we'll see in the next video. Till then, goodbye.